All right. So you've turned in homework 13, which was the inflation assignment. Homework 14, cost estimation, will be due 2 weeks from today. So a week from today, you'll be eating turkey and looking through the newspaper, deciding where to be on Black Friday morning. 2 weeks from today, you will have just turned in your last cost estimation assignment and maybe taking the final quiz of the semester. Today we're going to cover the additional 3 sections related to cost estimation. Remember that what these are is techniques to try and identify costs when we don't have all the data we need. You're always just kind of extrapolating on past experience. You're extrapolating on other projects that you may have data for that were in a different place at a different time and of a different size. So it's very uncommon that you'd be building exactly the same thing at the exact same time in the exact same location. And because of those differences in time, location, and size, we have to develop methods that enable us to project the data that we have to the circumstances that occur. So that's the idea of Chapter 15. By the way, this homework 14, that's not posted yet on MU Online, but that will be available later today. So you'll have just under 2 weeks to solve that assignment. Any questions on the announcements before we get into today's material? All right. Have you ever flown in an airplane and looked down and maybe seen something like this, a photo like this? It's a bunch of swimming pools, right? Of course, that's the only thing it could be, is just a series of swimming pools right next to the river. No, it's not swimming pools. You'd find that out the hard way if you hopped in. All right, this is wastewater treatment. And so in wastewater treatment, it's a multi-step process where you're trying to remove pollutants before they get into the river because it could cause contamination that harms the aquatic life, that reduces the quality of the water for the communities downstream that are going to be using it for drinking. And so these are aeration basins where you're intentionally adding a lot of oxygen to the water to try and allow the bacteria that are in the water to break down the pollution, which they'll naturally do. These are clarifiers where you put the water in and you allow the sludge to settle to the bottom, and whatever will float you skim off the top. So physical and biological treatment. And so this is a pretty large wastewater treatment plant. It's hard, I don't remember where I got this image of, but this is treating the water of a town of some magnitude. This isn't a village. It's not a tiny little town. This is probably bigger than Huntington's wastewater treatment plant. I've been to Huntington's and I don't remember it being quite this large. Here's a smaller one. And so this is the wastewater treatment plant that you'd see for a much smaller community where instead of many different clarifiers here, they've only got 5. One looks like it's maybe under maintenance or something. When we have a difference in size, sometimes there are non-linearities with respect to price. So what I mean by that is if you're constructing a really large wastewater treatment plant, you maybe get a different price per clarifier than the smaller community did. Because, you know, oftentimes if you're going to buy 12 of something, you get a cheaper price per item than if you're buying 1 or 2 or 3. I've mentioned that you can walk into Lowe's and see that on the shelf where they have contractor prices for some items, you know, like electrical switches or light bulbs, that if you buy 12 of something, they give you a slightly better price. And that's what this exponent allows us to account for, is that if we have the data on how much something cost of a certain size or a certain number, so that would be C1, the item that we know the price for. Q1 is the size of that item, or how many there are. So what we're trying to do is we're trying to say how much item number 2 is going to cost based on the known data we have for item number 1. And item number 2 is a different size, or there's a different number involved. And so we have the ratio of the size multiplied by the cost of the known item. But because of the non-linearity, meaning that sometimes you get a discount for buying a lot, but sometimes actually it's more expensive the larger something becomes. Occasionally when you're building something really large, it increases the complexity, and it maybe costs more than twice as much to build, for instance, a building that's twice as tall. So a skyscraper that's 100 stories has got to be a lot more sophisticated and strong than two 50-story skyscrapers. So that would be an example of where actually it's becoming increasingly expensive rather than cheaper for each additional increase in size. And so the exponent relationship x, if x is less than 1, that's called an economy of scale, where you have an advantage for the more you buy and the larger it gets. A diseconomy of scale is the situation where it becomes more expensive per increase in size. And then x equals 1 is just where there's no discount or penalty based on size. It just scales linearly. All right, so as an illustration, let's take the case of a water treatment plant. And the size of water treatment plants are often quoted in terms of MGD. Anybody know what MGD is? It's not Miller Genuine Draft. Million gallons per day. So this water treatment plant that we have the data for, the one that was built already, has a Q1 is 0.5 million gallons per day. That's how much water it can produce. And the cost of that item 1 was 1.7 million. And what we want to do is we want to find out how much a 2 million gallon per day plant is going to cost. So Q2 is going to have a size of 2.0 mgd. And then the correlating exponent, the relationship between size and cost, is 0.14. And that number doesn't just come out of thin air. Actually, there are tables, and it's been studied in construction, the general relationship between size and cost. And so here are some typical things in a water treatment plant, and you can see their correlating exponents. And for most of them, it's less than 1, meaning that there's an economy of scale. So an air blower, buying a really large high-capacity air blower, like if you doubled your capacity, it's not going to double the price because that correlating exponent is less than 1. But there's a handful of these things where there is a diseconomy of scale. A sludge drying bed, an aerated lagoon, a laboratory. And those diseconomy of scales, each of those items aren't a piece of equipment, but it's related to space. So the larger a space that's occupied, it becomes increasingly expensive. For instance, with the case of the sludge drying beds, the reason why it would maybe be more expensive, if you're doubling your size, you're going to more than double the cost, because in the area in the middle is now harder to reach. And so you're having to have more sophisticated ways to get at the area in the middle. All right, so back to this example. X is 0.14. And what we're trying to do is we're trying to predict what's the cost of item 2. So if we substitute into the equation, the original item that we have the data for was 1.7 million. And the ratio of size is our new one is going to be 2.0. Our old one was 0.5. And we take it to the exponent of 0.14. So I think everyone has calculators today. Will you tell me what is the projected cost of this larger treatment plant?
$2.06 million. 2.1 million.
All right. $2.06 million. And so if you look at it, the small treatment plant only cost 1.7 million. Excuse me, the small plant cost 1.7, but we quadrupled the capacity for just a little bit more because that correlating exponent is so low. What it basically would allow you, if you were the engineer here and your client was a city that was preparing a water treatment plant, you could go to the city and say, wow, you can really get a much bigger plant for just a little extra money. So you might as well make it a little bit big, a lot bigger. If you have any uncertainty about how much size is needed, err on the side of excess capacity, because additional capacity is very cheap in this case. Does everybody understand this relationship? Okay, I have an in-class exercise where you're going to combine this idea together with the idea of indexing. Remember, with indexing, what we're doing is we're correcting for time. So you can, in the same equation, you can correct for differences in time and differences in size. And that's what we're going to do with part 1 of the in-class exercise. And so let me hand that out. The backside of the paper has all of those correlating exponents for each piece of equipment. So what we know is the one that's being built is going to be larger, and it's going to be built later. And so since it's larger, it's going to be more expensive. And then since it's later and inflation has been occurring, it's also going to be more expensive. And so those effects are cumulative, and we can account for both of them simultaneously by having our index ratio and then the size ratio that's applied to the original cost of each component. So if we look at the cost of each component individually, the aerated lagoon is going to cost $12.4 million. The blower is going to cost about $700,000. The pump, $290,000. And if we add it all up in total, it'll be about $13.5 million as the projected cost. And so, this is a very, very different estimate than if we had just assumed a linear relationship between size and price. If we didn't have this data that told us about the correlating exponent, and if we didn't account for the change in prices over time, think about a construction company that's putting a bid together and doesn't know to correct for those two things. They could find themselves in a lot of trouble by putting in a legally obligatory bid where now they have to build the thing for the price that they've agreed to, and if they didn't have someone that knew about engineering economy, they'd be losing millions of dollars potentially on the deal. All right, or maybe not get the job at all if they wildly overbid. Any questions about this example? So that's an example of cost capacity, and you'll have a homework problem that draws on that. The next approach having to do with cost estimation is known as the factor method. And I'm sure that the factor method is something that you're already familiar with, although you may not know its official name. And let me tell you about something that I would do when I was living over in Dubai. One of the things I really love doing is going out to restaurants there because there's so many great options. There's food from India, Arabic food, Asian food, European. There's anything you could want except for Mexican. Don't ever buy Mexican food in the Middle East. It just doesn't work. So anything else and you're going to find world-class food there in Dubai. So what I'd sometimes do though is I'd find myself in a restaurant where unknowingly this is a super expensive restaurant and it just looked like an ordinary restaurant, but you get the menu and the prices are through the roof. I guess some of the restaurants are just intentionally, it's like the Bugatti of food, or like a Lamborghini of places to have dinner tonight, and it's just showy, expensive prices. And I try to avoid those spots because there's so much good food that's cheap. And so rather than looking through the whole menu, what I learned was a shortcut for quickly identifying if this is going to be one of those ridiculous restaurants that's super overpriced, is just look at the price of a bottled water. Because at a good restaurant, the kind of place that I like to go, you could get a 1.5 liter bottle of water for about 2 dirhams and 50 fils, which is 75 cents. You get a big bottle of water for 75 cents at the restaurant. But you go to one of the expensive restaurants right next to the Burj Khalifa, and that same 250 water could cost 25 dirhams. And so now you're talking about like almost $7 or $8 for a single bottle of water. And so then I just, before going in, I'd look and see, all right, what are these guys charging for water? Oh, I'm out of here. And save myself the humiliation of getting the menu, looking through it and saying, bye to the waiter. All right, so that's an illustration of the factor method, which the core of the factor method is sometimes you can project the cost of an entire project by just looking at the cost of one component individually. So if the whole project is the meal I'm about to eat, what I could know is the meal is going to cost about 10 times what I spend on the bottle of water. And so if I see that the bottle of water is $2.50, the whole meal is going to cost me about $25. But if I see the bottle of water is $25, that means the meal is going to be $250. So that's just kind of a rule of thumb that I developed. And the same thing holds true for construction of new homes, for instance. A rule of thumb that a lot of people use is for a used home, maybe you should expect to spend about $100 a square foot. In a lot of markets, that just happens to be the case, that if you know one thing about it, you can project the entire price based on that one constituent. And so the factor method says that if you know the cost of some individual component, one piece of major equipment, then have a multiplying factor, H, you can estimate the total cost from that. So I've illustrated that my H factor when it came to a meal was multiply it by 10. All right. Now, there's another thing that we can also, in a similar way, account for, and that is the indirect costs. Remember, the indirect costs are those expenses that we can't directly tie to the level of activity. So accounting, or supervisory, or the cost of rent, for example. You don't know how much rent specifically is required to make a single Twinkie because it's a fixed cost that doesn't vary with the level of production. So there are these expenses that we have to recover in an indirect way, and these indirect cost factors can be a percentage of the overall project. In the same way that H is a multiplier to find the cost of the entire project based on one component, we can also account for the indirect costs by just adding it on to the end. And so here what this equation is saying is that you have the cost of one piece of equipment, and then you'd multiply that by the sum of all these direct cost factors. Like if you know that in a typical job, I think in our handout that we have for today, the example has to do with a generator. So there's all these other expenses. When you put a generator in service, it's not just the generator itself, it's the concrete pad that it has to go on, the training, and we just know that generally the cost of those things is somehow related to the overall initial cost. And then on top of it, you have to add the indirect costs as well. So in part 2 of our in-class exercise for today, what I'd like you to do is consider the factor method and that formula that I just showed you on the previous slide. Let me paste it over here so that we can see them both at the same time. All right. So what we're saying is we're going to use the factor method and also account for the indirect costs simultaneously. So we know the cost of one major piece of equipment, the generator itself, but then there are also the other expenses of the concrete pad, which is usually 39% of the cost of a generator, and training is usually 16% of the cost of the generator. And then on top of it, so the bracket means that once you find that overall direct cost, you add the indirect costs on top. Okay, so we have to pay $975,000 to buy the generator, and then 39% of that to pour the concrete pad, 16% of $975,000 for training, and so the overall direct costs are going to be $1.511 million. Those are all considered the direct costs that that's outflow that we have to spend in order to get the item in place. But on top of that, there's also the indirect costs having to do with the people that placed the order, the expense of whatever supervisor or coordinator or maybe engineering services are required to initiate the project and get it installed. So the indirect costs are applied to all of the direct costs, and that means that we should have $1.92 million available to put the generator into service. These are simple ideas, but when you have all of them together, it gives you kind of a very powerful set of tools for coming up with accurate cost estimates. The idea of if you failed to account for the indirect costs, that can really make people pretty agitated. You know, here at Marshall, for instance, when we do research, if we get $1 million from the National Science Foundation to do a research project, almost half of that goes into the university's pockets, and they use it to cover the cost of being in the building, electricity, managing the contract, and keeping track of like the budget inflows and outflows, so purchasing and so on. So indirect costs have to be recovered, or else the infrastructure isn't in place to administer the grant. Any questions about the factor method? Now on the exam, there's going to be the final exam. It's a cumulative exam. It would be impossible for us to have an exam that wasn't cumulative, because over the course of the semester, all of the ideas just build on each other. So for instance, today your exam used the equation method. So you still have to know those things from way early on to do the more sophisticated analysis. But even though the exam is comprehensive, there's going to be additional weight in terms of the points that are available to be earned. There's going to be a disproportionate number of points that are weighted on the material since the second midterm. So you could see a question from any time of the semester, but there's going to be relatively more questions of the more recent material and more of the points from the more recent material. And so it's a virtual certainty that you'll have a question on the final exam having to do with at least one of the things from today's in-class exercise. Let's talk about some general characteristics of money, the reason why we have money, and how you know if something is money or if it's not money. That seems funny to say, but it's coming up for debate these days because we're starting to use alternative currencies. I'm sure you've heard of Bitcoin and other cryptocurrencies. And so when we go through this list of characteristics of money, think, is that true of an electronic Bitcoin? Is it true of like a gold coin? Is it true of a dollar in your pocket? So money should be durable. It means that it can't wear out, or else it's not very useful as money. So you couldn't use a peanut butter sandwich as money because it's going to get smashed if you put it in your pocket, and it's just naturally going to get moldy or dry out or something. So a peanut butter sandwich wouldn't be good money, but a coin is pretty durable. Paper, a little bit less durable. Even coins wear out though. So if you think about electronic money, that's really durable because it's just bits, so it withstands physical and wear and tear. It doesn't wear down at all. So portability. How easy is it to take gold coins? Well, there's a lot of value in a gold coin, but if you were going to pay for a football stadium, you'd have to take wheelbarrows of money to get millions of dollars. And so the portability of something like gold, or if you've seen any of the heist movies where they're taking sack after sack of money and it's really heavy because they've got $100 bills, but there's so many of them that it's tough for them to move as much money as they're trying to steal. Even physical money has limits on the portability of it. And so again, electronic currencies make it a little bit easier to take the money with you, where your Bitcoin wallet could be recoverable just by memorizing like a phrase or a series of words. Divisibility. It has to be easily divided into smaller denominations. And so, with cash money, it's pretty easy to do that, but occasionally you'll find yourself in a situation where maybe the cashier doesn't have the change that they need. You go to Dollar General and see a sign up, a handwritten sign, we need $5 bills, something like that, because just there can be an imbalance in the change that they've got. Or a gold coin. Does anybody know what the cost of gold is per ounce? It's about $1,200 an ounce. So if you have a 1 ounce gold coin, you can't saw that in half if you want to buy a Rockstar energy drink. There isn't a gold coin small enough that it's easy to pay for a small thing. Like even a 1/10 ounce, that's the smallest. The U.S. government mints some gold coins, and the smallest one they mint, I think, the smallest one is 1/10 of an ounce. But even that is going to be worth about $120. And so it's not, gold coins aren't easily divisible. But other things can be useful for micropayments. The idea is that in the future, journalism might be supported by, like if you offered a half a penny for every article you read or every list that you looked through, then that half a penny per person would be enough so that then we didn't have to have our data bought and sold by information companies, or you didn't have to see ads. And so micropayments nowadays are limited by the fact that the smallest transaction you can do with a credit card is about $1, based on the fees and the expenses that a merchant gets charged. If a transaction is less than $1, then it's really tough for them to come out ahead. But electronic payments of the future are going to be more easily divisible to enable micropayments. Uniformity is important because we expect that $1 bill is as good as the other one, but that hasn't always been the case in the past, where sometimes in the past there have been private banks that have issued their own currency. And so then a dollar, a so-called dollar from some small bank in a remote country town wouldn't necessarily be as appreciated and valued as a dollar issued by a bank in a big city that maybe had a longer history of being in business. Limited supply. Remember that money gets less valuable if the government starts to indiscriminately print a lot of it. And you've probably seen pictures during the Great Depression of people taking wheelbarrows of money in order to buy a loaf of bread. And in our recent times, a similar thing has happened in Zimbabwe, where they've had runaway inflation because the government just didn't limit the supply of the money. Back to the example of Bitcoin, there's, I think, a limited number of Bitcoins that will ever be mined. I think it's something 20 million, 26 million. That's the maximum number of Bitcoins there will ever be. And so there's a built-in limit to how much supply there can ever be. But in terms of acceptability, Bitcoin is essentially useless. There's so few places you can go to spend it. You couldn't buy a gallon of gasoline here in Huntington. You couldn't go for lunch in Huntington with Bitcoin, but dollars are acceptable almost everywhere in the world. I've never been to a country where people weren't glad to take dollars. And sometimes it's more convenient to exchange it into the local currency, but we're kind of fortunate in that our currency is considered the reserve currency for the entire world's economic system. So these are just some of the interesting characteristics of money. I'd encourage you to read through the part of the book that talks about the basics of money, because understanding what money is can give you insight into the future. Currencies like Facebook's Libra, I think Google is thinking about starting its own cryptocurrency as well. And so understanding more about the characteristics of money would help you to be ahead of the curve as money and what we use as money changes throughout the future. Now, back to, since we're doing terminology, let's revisit the difference between what is an indirect cost and a direct cost. And so direct costs are those things that have to be present in order to generate a certain output. So the supplies that go into manufacturing, the materials, the labor. But then the indirect costs are the things that you can't directly tie to how much is being generated. So I found this online and I thought it was a pretty useful illustration of the difference between direct and indirect costs, since those are some terms that can sometimes remain a little bit ambiguous. So recovering the indirect costs we can do by applying that factor on top, like we did in the recent in-class example that we just did, and the money that's collected there would go towards the taxes, the heat, the power. But if you have a really large organization and you're trying to figure out how much indirect cost you need to recover, then what you could do is you could look at a basis for allocation. So for instance, if you know that a certain division in your company uses a lot of floor space in a warehouse, then you might expect that particular division of the company to to cover a disproportionately larger amount of property taxes, since property taxes are often paid on the basis of space. Or for instance, power. If your company has power costs that it has to pay the electric company, then what you could do is analyze inside of a factory which products are plugged into how many different electrical stations, or you could actually monitor the electrical use. And so some of the things you sell maybe have a very low embodied energy requirement, and other things have a high embodied energy requirement. And so recovering those indirect costs can be tied to how much input, how much of each of these inputs is required to generate them. And that's the idea behind in-class exercise part 3 on the handout that you've got there. What we've got is a company that has 3 subdivisions. Our construction company does excavation, they assemble reinforcing steel, and then they also do surveying. And of those 3 divisions, you can see that the largest in terms of the employees is the steel assembly. That's a very labor-intensive activity, and so we've got a lot of employees. We know the revenue for each of the subdivisions of the company, the number of active projects that are currently ongoing, and then a little bit of additional data about them. And here's the bottom line. The holding company that owns these 3 different subdivisions has a bunch of indirect costs that it has to recover. And what they're trying to decide is how much indirect cost should they make each of the 3 subdivisions cough up to the corporate office. You know, it's about $6.95 million, and so should they just divide it by 3, and each of the subdivisions has to cover a third of the overall indirect costs? Or is there maybe a more equitable and more reasonable way to decide how much each one of those 3 subdivisions is going to have to pay? So in steps A through D, what we're doing is kind of stepping through that decision analysis of trying to figure out how to allocate the indirect costs. In other words, of the $6.95 million, if you look at the revenue, meaning how much income each one of these subdivisions has, if it was proportional to the revenue, then how much would each of the 3 divisions have to pay? All right, so let me pause for a moment and give you time to read through steps A through D and think about how are we going to get that $6.95 million to the corporate office. So if we say that the total indirect cost is going to be allocated on the basis of how much money each of the 3 subdivisions is bringing in, then you can see what each of their share will be. The surveying group isn't going to have to pay as much to the corporate offices as the excavation group because they're not bringing in as much revenue. And so their overall proportional share is just on the basis of what fraction of their revenue is to the total revenue for the company. And then for steps B, C, and D, all we're doing is we're looking at what kind of work do each of those 3 subdivisions do. You know, if they're going to pass along the indirect cost to their customers, how much of a surcharge will they have to add on top of their normal direct costs, their normal prices plus a surcharge, to be able to cover the indirect costs as well. We're almost out of time, and so what I'd like to do is show you the solution to the last part of the in-class exercise, just so you have an idea of what's the main point to activity-based costing. In activity-based costing, what it is you're trying to figure out how much of the indirect costs should be going to each of the parts of a company that generate the indirect costs. And so there's some terminology here related to what is a cost center, what are the activities and the cost drivers. That's important to memorize those terms because it'll allow you to interpret a problem statement. But in the in-class exercise example, what we were doing is we were saying that to do IT support costs $145,000 a year. And this is just another case of you're trying to figure out, of the $145,000, how much should each of these three divisions be expected to pay. Sometimes it's just not as simple as dividing the bill by 3. Like if you've got roommates and one person loves to crank up the heat, maybe they should pay a little bit more of the gas bill than the rest of you who are willing to put on a sweater. That's kind of the idea here, is you look at what activities are actually driving the costs, and then you recover the costs according to the level of activity. And so here in this illustration, what it was is we were looking at if you have engineering, safety, and computer science, and it looks like the safety is a small program, only 4 faculty compared to 12 in engineering, but if we were going to just allocate the costs based on the faculty, then you can see that this one's support calls. We don't actually do it based on faculty, but on the case of the support calls, computer science, it looks like they would have very few support calls. Presumably they can solve some of the things themselves, whereas the other people can't. So this in-class exercise was just trying to look at, of these costs, how would you decide to divide up the pie of how much each group has to pay? And so the engineering people may say, well, let's do it on the basis of the number of computers that are used by each division. And that would make their bill the lowest. Whereas the computer science people would say, no, let's not do it on the basis of computers that are connected. Let's divide up the pie of who has to pay the bill on the basis of support calls per week. And since their support calls per week are relatively low, then that would mean their bill is the lowest. And so, I mean, maybe the fair way to do it would be to come up with a weighted model that used all 3 approaches and somehow took the average of the 3 different costs that each one would have to bear. But the main idea of activity-based costing is that when indirect costs have to be recovered, you'd use their underlying activities as the basis for the allocation. Okay, so just to reiterate our announcements from earlier today so that we're on track, you're not going to be here next week, and neither am I, but 2 weeks from today, homework 14 will be due, and we will have a quiz either Tuesday of next week or Thursday of next week. And now it's 9:17. I've stolen 2 precious minutes from you. I'll pay it back with interest when we get back from break. All right? Have a good vacation. Ooh, it's continuous compounding at a very low rate. It compounds daily, but the interest rate is 3%.